So Dr. Keeling's going to speak first, and he's going to talk to us about mankind's reliance on fossil fuels, anticipated and unanticipated consequences. And those of you with SAUVs will hopefully turn them in after Dave talks. And he'll answer a few questions, and then I'll introduce Dr. Thompson, who'll talk to us about rapid climate change. Thank you.
Thank you very much.
Some water.
I'm very pleased to be here today, and of course I feel very honored to be recipient of the Tyler Prize. One of the unanticipated consequences was that I wasn't able to make a talk that was really effectively about unanticipated consequences. But I will give as a preamble to my talk that once I gave a talk which I thought I'd try to give a sequel to now, and this was in 1969. That's more than 30 years ago. And I had a chance to talk before the Philosophical Society, and I thought I'd give a philosophical talk. So I was thinking about consequences of what man is doing to the environment. And so I'll read this first little bit here. Today this was the end of that talk. Today we hold widely divergent views concerning possible peril. Have you noticed that practically all master plans do not project beyond the year 2000? Our college students, however, today expect or hope to live beyond that date. Now, the reason for that was the People's Park and the riots of the Berkeley students and other things were on the minds of people at the time that I gave this talk. Almost every time you think about the long-range interests of the human race, you actually end up focusing on some small part of it. And that was the student riots. So it got into the sentence here. It was immediate danger than it is today. If present trends are assigned, mankind's world will be in a greater immediate danger than it is today. Immediate corrective measures, if such exist, will be closer at hand. With that, would you please show the first slide? This is certainly an example of an unanticipated consequence of having a perception of a peril, that we know astonishingly little about every aspect of the environment, from its past history to its present state, to how to conserve and protect it. That's the state of affairs according to Michael Crichton, who's written a bestseller book that some of you have looked at. Well, with that background, I think it's worthwhile to suggest that maybe we don't know very much, but depends on the length of time you're thinking about. Suppose you think about these three people, George Washington, Franz Joseph Haydn, and James Boswell, who lived in an age when there certainly was a sophisticated human race on the earth. But when they were children, all we knew about the environment was that it was made up of earth, air, fire, and water. The atmosphere was perceived, but nobody had any idea about what it was made of. Carbon dioxide was not known. Now, this is what happened during the lifetime, a single lifetime of these people, a 50-year period essentially, when Joseph Black discovered that there was something in the air that would come out as a precipitate in an alkaline solution, properly prepared, and he called it fixed air. And it was the first discovery that there was something about the air which caused it to have different properties depending on what you did with it. Then over this period of time after that, these people came along, and before that time was over, hydrogen and oxygen and nitrogen were all discovered in that 50-year period. And that changed the whole feeling about what the atmosphere was like. Imagine that when you were living as if you were living as a child like those three people, and you saw a tree, you had no idea what the leaves were for. You didn't know how the tree got its sustenance. So alongside this chemistry of discovering what was in the atmosphere was also this fantastic discovery of photosynthesis and how plants actually operated one step after another. I have the names of what they called it. Here's Priestley, who believed that there was something that turns out to be oxygen. If it was the lack of oxygen that was the name given to it, phlogiston. Now that's about as complicated as it can get in your mind. It's something, absence was causing this. But anyway, the air was injured by plants. This is a doctor, Jan Ingenhaus, who in a rather short time took time off from his work in Central Europe and went to England and came across the discovery that plants needed light to grow. Imagine, nobody had figured that out before. And at first he had to call green matter something that was formed in pure dephlogisticated air. Phlogisticated air, that was the vocabulary of the time. Then comes a Frenchman who found that the plants needed the fixed air that Joseph Black had discovered. Ingenhaus came back with another paper in which he showed that the carbon from the air formed carbonic acid. The sophistication of chemistry was going on at that time. And finally, Théodore de Saussure came along in the beginning of the next century, and that was the beginning of the quantitative understanding of carbon dioxide. Now, the measurements of carbon dioxide worked their way through a whole century, practically, from the first measurements of a very capable man, Alexander von Humboldt. But I suspect that when he said it was about 1%, that was not a very careful experiment that he was able to put off, and he wanted to cover himself as best he could with something that looked like it was a real measurement. Certainly it was a trace element in the atmosphere. John Dalton, all of you who have taken chemistry know that he had an important place to play in chemistry, and he came up with a number of about 680. And then Théodore de Saussure came along, and he kept plugging away at this for 15 years and brought it down to about half of what it was before. And finally, in 1870, the right answer was actually obtained. It was obtained by great brute force, a huge machine that was pulled by horses to the coastline of Belgium, and in there was a tank, and by discharging the water from the tank and sucking air into the tank through an alkaline solution, he was able to get a whole bunch of carbon dioxide, and then he could measure it to a precision of 1 part per million. So already before the end of the 19th century, it was possible to get measurements almost as good as the measurements today. But it didn't happen that actually took place, because the next thing that happened was people wanted to streamline the measurements. So they came up with various methods which could have gotten the right answer if you took enough time to make the absorption take place. But by the 1920s, hardly anybody was thinking about this subject anymore. A steam engineer in England named C.S. Callender, who was also working with the coal industry, became concerned about this issue because people had talked about the greenhouse effect already in the 19th century. And he pondered that carbon dioxide was going up at about the rate that fossil fuel was being burned based on all of these measurements. He discounted the early ones quite sensibly, but the ones he considered that were preferred measurements included Jules Rice was right down here, the lowest measurements practically. By the way, this is a very broad scale we're looking at. But by the time that he came up to where he was writing this analysis, which at first only covered this amount of material, he was well above what's actually the present value at the time. Then came along a man who did some very important work on the chemistry of seawater, for which we're grateful, because he measured how bicarbonate and carbonate combined and had to do with the partial pressure of CO2 it exerts between the atmosphere and the sea, in a PhD thesis around 1915 to 1920 when he was working on it. And when I became interested in the carbon dioxide and looked in the literature, this is what I found, was that the belief that the carbon dioxide varied by more than a factor of 2 from the polar regions to the tropical regions. Another development that took place was in meteorology, and Carl Gustav Rossby, who had learned meteorology in Scandinavia, were pioneers at studying weather forecasting, came to the United States and set up a program. But then he went back to Sweden, where he had his origins, and started a program in meteorology which included measuring atmospheric chemistry. And using the methods that were in vogue at the time, they came up with the idea that carbon dioxide was spread in such a way that you could use it sort of like forecasting weather. You could see patterns of highs and lows in carbon dioxide, and you see these numbers are varying again by at least 50 parts per million on a single day. And there was no question, I believed this at the time. When this work was published, where would you expect to find results? And people that were advising of what might be done said there's no reason to make extremely precise measurements because you've got this huge spread anyway. But what I did was, working at the California Institute of Technology, I took on a program which is sort of a what if, just to do something that would give me a handle on studying the environment. So I worked on measuring carbon dioxide in air and water to see to what extent they were in equilibrium with each other. And because I didn't know what to expect in the air really, I decided to make the measurements over a diurnal cycle. And at that time I was using chemistry terms. This is mole fraction in percent. ppm hadn't really come along yet. Those other slides are just interpreted that way. So what I saw was that it would be lowest in the daytime, go up at night, and come back down. I read a book by a physiologist in Sweden named Heinrich Lundegard, who talked about why that would take place, that the air at night is close to the ground, is stable, and the carbon dioxide can emit from the soil and go in the air and build it up. Furthermore, isotopic measurements were made because I was at the California Institute of Technology, and it was the newest thing was to measure isotopes. And Sam Epstein there, for example, said, be sure to make some measurements with carbon-13 as well. So what it turned out was that the carbon-13 was doing the same pattern because of a signature of the isotopes, which was transferred to showing that what was causing this to happen was carbon dioxide from plants. Now here's 4 of about 8 records I was able to create that first year. I could make maybe 1 or 2 measurements a day in the laboratory by the methods I was using. What struck me was I wasn't seeing this big spread in the background numbers. They're all sitting there just under 0.32, somewhere between 15 and 20 parts per million. The next summer, well, actually the next March, I finally decided I'd try to figure it out by looking at some area where it was the most undisturbed area I could get close on. The White Mountains of California, which are east of the Sierra Nevada, had a station that was run by the U.S. Navy, of all people, of all organizations, which was studying physiology at high altitude. And I was able to be transported up to this station at 12,000 feet in March, and by having talked to meteorologists, I picked a time of strong winds. The winds built up to about 40 knots here when the cold front went through, and for 5 days these measurements took place, and there it was, sitting there just under 320 parts per million. The result of that was, when I showed it to people at Caltech, there was somebody there who worked for the Weather Bureau and said, you ought to show this to my boss, Harry Wexler, in Washington. So I got on the airplane for the first time in my life and flew to Washington, saw Harry Wexler. He looked at this high altitude record and said, well, we have just set up something out in Hawaii which is almost as high as that. He proposed that measurements be made at Mauna Loa Observatory at 11,000 feet. By the way, the quotations are replete in the literature that these measurements were made on the summit of the mountain. They were not. I mean, 2,000 feet below on the slope of the mountain. Gives you an idea of that when people pick up interviews and then it's passed on to somebody else, you always have the feeling if you've been the person interviewed that you're not getting quite the story across that you thought you did. So this record then prompted the Weather Bureau to propose that these measurements be made elsewhere. But something else had happened. the physicists had gotten together and decided to have an important program to study particularly the ionosphere, but they decided, let's study the physics of the globe in many ways as we can. There was enough funding at the time, and the International Geophysical Year came along. And as a result of that, I had a chance, which was really a rare thing to have happened. I was in my 20s, and I asked for an extremely expensive instrument to take place of the tedious way I was doing it. These instruments cost $10,000 of 1956 dollars, and we got 4 of them out of the IGY program. And with that, all these measurements were made in the next 4 or 5 years. Many of these are only one-shot cruise transects, but over here enough were made to look at the cycle in considerable detail, what was happening with carbon dioxide, both in time and with space in the Pacific Ocean. And the first measurements that were extremely detailed were at Mauna Loa Observatory, where we put an instrument right there on the spot to make measurements all the time. And here were these measurements, to my great surprise, or certainly the surprise of the person who was there, because I suggested it would be about 315 parts per million. It turned out to be that. Now, if you think about it, the previous year, it was the month of March that they were being measured in the Inyo Mountains, and here we're getting the same answer. So it looked like that we had a background error value that was stuck around that. But this was a struggle to get the station running. They had a 5-kilowatt generator to take all the power, and the generator broke down at that point. I had to wait about a month, after which there it was. It wasn't constant. Something else was going on. There was another power failure. Then these data came along, and then there was the last power failure before they finally got enough. Even with the IGY, they didn't have enough money to buy a good generator until they made a special budget for it. Now they were up to 10 kilowatts. They actually had a pair of them, so if one went out, the other one could be turned on to do the whole job. Now unfolded something that looked like this. Now, there's a rule in statistics that you don't want to believe in a cycle unless you have at least 5 cycles. But actually, that told the story. Because it was sufficient amount of information, it was pretty clear that there was this cycle. And although people had claimed there were cycles, they never found that cycle. They found one which was in polluted air in Paris, for example. And that didn't peak in the springtime. It peaked in the middle of the wintertime. So taking those other measurements that I described from the IGY and putting it all together, we now changed what Book had said from 150 to 350 parts per million was in this narrow range here, this being the difference between the highest values in the springtime and the lowest values in the fall. So we had defined a cycle. Now, with that background, I went ahead and continued these measurements because I found them interesting enough that each year something else happened. But I can't talk about every one of these years in detail. Though here's that first one with some missing data, and it very well covered up in this graph. Hardly anybody notices that it's missing. But I also was involved with the South Pole as part of IGY, and that program has continued to the present day. And when people talk about the Mauna Loa record, they hardly any of them realize there was a second record which is run even longer, goes all the way back to 1957. But these two records together tell you quite a lot. They tell you that the oscillation in the northern hemisphere is opposite phase from the southern hemisphere because the plants grow the opposite time of the year for the seasons. It's also, you notice here, that carbon dioxide rise, which this audience knows had something to do with the burning of fossil fuel, adding CO2 to the air, that the South Pole record wasn't rising as fast. There you can see it without any manipulation of the data. The cycle is down at the bottom of the range of Mauna Loa at the end of the record, where it was in the middle before that. So there you see that the fossil fuel, of which 90% is discharged in the northern hemisphere, can't get to the southern hemisphere fast enough to prevent a buildup of the gradient as the fossil fuel itself builds up. So here's a chance to see firsthand man intervention into the natural cycle of the carbon. I was once at a meeting, and there was a poster at this meeting, and a woman from the Department of Agriculture had the Mauna Loa plot on it, and a meteorologist from Pacific Gas and Electric was talking to her, saying, you know, 40 cars come up to Mauna Loa summit to the station every year, every day. And he was under the impression there was only one station, and it was a result of automobile traffic that was causing this curve, not understanding that there was a South Pole record where there weren't any automobiles. It took a long time to get back to isotopes, and this was a logistic problem, or a management problem. We had the instrument already built at the IGY to measure carbon-13, but the program took so much trouble to keep it going that the isotopes didn't get done until Professor Wim Molk in the Netherlands came to me one day in my home in California in 1977 and said, I have a graduate student whose name was Peter Tans, who I'd like to send out to you and get the isotopes back into the program. And so that was done, and the isotope records began there. Funding was always a problem, and there was no money to pay for it. But the measurements were sent over to the Netherlands, and the Netherlands laboratory paid for the measurements so we could make them finally. What you see here is that it's so similar to this curve here. It shows that plants were mainly responsible for those patterns that you see. Now, just to summarize the rest of my measurements, eventually we set up a series of stations, and somebody said that I have the credit for that, but actually the credit goes to just about everybody who did something. Many of these stations are NOAA stations that were set up. Certainly IGY paid for the South Pole and the polar programs of NSF. This was done by cooperation with the New Zealanders, who also ran Kermadec. This was a NOAA station. This is really our own invention to get to Christmas Island. Kumakai was our invention, too, to simply get measurements made on the coastline because we had ships going back and forth. We wanted to have sea level measurements as well. Certainly that's ours. But Point Barrow, again, was a NOAA station, and that's a very important station up there, which almost lost its funding a few years ago and took great efforts to get the Canadians to find enough money to keep it going, because that gives us 2 stations in the Arctic. Now, I should say that this program has survived, but NOAA has now something like 100 stations that are measuring CO2, and some of them are measuring isotopes. Probably quite a few of them are, but they're having to struggle to get the data worked up because it's so much work they want to get the data for sure, but there just isn't enough funding to get the data caught up in time. But here is a summary. Detrending these records differently for carbon-13 and CO2 shows you that there's some kind of oscillatory behavior which is seen in all of the stations to a certain extent. You see how similar the wiggles are at the South Pole and at Point Barrow, Alaska. You can also see, for example, that at the tropics, that this curve is creeping away from its more central position, closer to the Arctic one. Now that suggests that CO2 is being emanated not by fossil fuel, but by something at the equator. But this is controversial. The people that are publishing about this now, who are not using isotopic data, which shows the same effect, are not finding that the tropics are a greater source. And we are struggling to see whether we have some artifact where we can't prove whether it's oceanic or terrestrial. It looks like it's terrestrial, but there's enough complications with the isotopic measurements that it might be due to something called an isoflux effect, which I don't have time to discuss. But the point is that we're getting closer to microcriton, that we really don't know very much about what's going on. Now, to go a little bit further in the analysis, this is the CO2 record. You can look at it so many different ways. It looks just like it's smoothly rising there. And these are data that were collected by proxies from ice cores. This is important because it shows how fossil fuel wasn't responsible for some kind of rise in CO2 before a certain point, but it took over in terms of the amount of CO2 that's accumulated in the air against how much was put in the air as a cumulative function. if you look at it in terms of the rate of change, this is exactly the same data, but it's the rate of change in the data. Now you see all the swings going on when you emphasize it on this particular plot, which didn't show on the other plot. Now, one way to look at this is to take this Mauna Loa record without the seasonal cycle being shown, suppress it, and compare it with the trend in fossil fuel, which is discounted to the effect that it makes the best fit it can here. And it's absolutely remarkable how close the curvature of that follows the actual rise in CO2. Here's the South Pole doing the same thing. Let's take those two records and combine them and look at the anomaly. Now we see boldly with the data itself showing these wiggles of going up and down that are second order to the main idea of the rising, but is still telling us something. Now, we became conscious that whatever those wiggles were, they probably have a manifestation in temperature because El Nino was a process that we identified with them. El Nino events that take place in the Pacific Ocean, change in the trade winds, cause, usually on a global basis, causes it to get warmer. Some areas get colder, but in general it gets warmer. And what you see here is, this is the record of global temperature, which, by the way, none of this was available at the beginning of my program. The struggle to get global temperature took about 25 years, half of the time we've been here, before these numbers actually were available for anybody to look at, in spite of what Michael Crichton is saying. But here's an example of a very important El Nino event in 1877, which is beautifully represented in the data which came from the British Admiralty and other places and were collected and put together, mostly by the people in the United Kingdom. I just give an example of three important El Ninos. This is the one that's fairly recent. Now, if we filter our data to look at the El Nino timescale, take out all the other variability and just look at that, you see how closely it seems to be related to temperature. However, that's done on the accumulated amount. Now, if you take the rate of change of the CO2, this is the first derivative of those who have mathematical background. Now you see that there's a closer connection that when the temperature is warm, the rate of change of CO2 is maximal, typically during these El Nino events. Now, going back a little ways, we hadn't gotten that far in Mauna Loa records. In the early 70s, somebody suggested that there was a decadal variability in the CO2 record, which correlated with sunspots. And that set us going. You can't imagine how much of what we do is a result of somebody else thinking of it first. Although there's not, we aren't the only investigators that have that happen to them. So here is our attempt to look at the decadal variability in temperature against CO2 updated to the present. And it certainly looks like there's a plausible connection. So now let's try something in which we are innovating compared with what the meteorologists are doing. We use something we call a spline fit because the irregularity of the CO2 record doesn't really allow to do a careful spectral analysis where you have oscillatory behavior that's fixed in its phasing and amplitude. So here's a fit through the data of the temperature. And this is an embarrassing picture because there are people, including those who reported to the IPCC, the Intergovernmental Program for Climate Change, in their third assessment, on what's been called the hockey stick, in which they said temperature has been pretty much constant until just recently when it zoomed up. But what's going on here? Here's the 1920s, and here's happening again, and here's a period in between. It certainly casts doubt that the greenhouse effect is responsible for all the warming, because it can't possibly be responsible in the same way for these two warming events. Now here's one where we loosen up the spline, and because it's not spectral, we can see wiggles in here which don't exist in this part of the record, or very much in that part. In other words, when it was warming, these wiggles weren't there. These are bidecadal in their periodicity, and they're coming during the periods which are stable and not rising. And Here's one that's got wiggles on the decadal time scale, and it's this curve, which is the basis of the ones I already showed you. Now, suppose we take those three versions of it, and we take one against another. We get what we can still call a bandpass, which is used in spectral analysis. But the decadal bandpass looks like this, and this is the one that's lower frequency. Then we'll just talk now about this one. The strange thing about this one is that although it's decadal, it's not 10 years in a consistent manner. Now, go back to the proposal that CO2 was connected with sunspot cycle. The carbon dioxide did something for us. It told us that we should look for decadal variability. And this decadal variability is, as far as I know, not published by anybody but us, because we're violating most of the rules of doing it spectrally. The spectral analysis doesn't come up with a very clean understanding of it, as far as we can tell. But here's in the 19th century, when the sunspots are low, it was warm. And the argument was that when sunspots were high, they covered up the sun, and therefore the sun wasn't as hot. And this was published at the time. It was believed as a connection between sunspots. Then there was a period of time when people scoffed the whole picture about sunspots. There was Lake Victoria, which its level went up and down essentially with global temperature. And they published that Lake Victoria was correlated with sunspots in its level. And then it stopped happening just after they published the paper. And it happened just about here. And here, but then along came a new era with people like Harry Van Loon, who discovered that there might still be a decadal cycle correlated with sunspots. And his work really took off about this time. So here we are now with the sunspots, but we have a new theory. And the theory now is that when the sun has sunspots, it's more active, so it's hotter. What about this period here? This turns out to be a 6-year oscillation. If you notice, it's during this period of warming that the 6-year cycle is existing instead of the 10 and the 20-year cycle. So I'm going to stop there, but I just want to say that this is where Crichton comes in. We still don't know that much, because right now the fashionable idea is that the solar cycle of sunspots is somehow involved with global change. And I think this is a pretty adequate proof that it can't be true in exactly that way, because it seems to come and go with something else in the middle. This is about a period of warming. This is a period where it's essentially level, although it's breaking down now because probably the greenhouse effect is taking over as the most important aspect of it. So, yes, we've been able to make some progress, but there's a long way to go. Thank you. Thank you.